Alright, in this video, we're going to expand on right-hand rule number 1, and we're going to look at right-hand rule number 2 and 3. Doesn't that sound like fun? Alright, so these conventions are still the same. North is towards the top, south towards the bottom, east, to the right, left is west, into and out of. So those are still the same as before. Just repeating them, making sure that they stick. So right-hand rule number 1 deals with the force on a moving charge when it's in a magnetic field. Okay, so if you have moving charges, also known as a current, because current is just a whole bunch of moving charges. Near a magnet, it'll attract, right? There'll be some sort of force, an attraction or repulsion, depending on the direction. This happens because electrical currents produce magnetic fields, right? Magnetic poles are attracted to each other because they put out a field, or repelled from each other because they put out a field. Electrical currents also put out that field, which makes complete sense when you think about what a magnet is. A magnet is a bunch of charges, electrons, spinning or moving in the same direction, also known as what a current is. A bunch of electrons all moving in the same general direction. Okay? Makes complete sense. That highlighted one, perfect sense. Now, moving charges feel magnetic force, and that's what last lesson was about. That's what the right-hand rule 1 is about. Those moving charges, or the currents, in those magnetic fields feel force. Okay? Not all magnetism is a result of magnetic substances such as iron. Because of that close relationship between current and fields and magnetic fields, some magnetism is produced from electrical current. And you'll see and learn about things like maglev trains, which are the trains that levitate. Those happen because of the magnetic fields produced by current. Okay, so moving charges produce magnetic fields, which means if, let's say, I have a wire with a current in it. Okay, a wire with a current. It's going to produce a magnetic field. A straight wire produces a circular magnetic field. Okay? So in other words, if I had a wire like right here, going straight through the page, there's a magnetic field going around it in a circular pattern. And the farther away you get, the less strong it is. But you can see that these were iron filings, just randomly placed, and then you put the current in there, and it created them in a nice loop. Okay, so straight currents produce circular fields. If you have, let's say, a single loop, so if you have a loop of a wire, so I take a wire and I just make a nice little loop about it. What happens is, around each of those sections, every infinitely small section, there is a loop of the current. Okay? All pointing in the same direction, all looping the same. If we take multiple of those loops and we put many loops together, we get what is known as a solenoid. Okay? So let's say I have a wire and it creates a loop around it, right? So it creates a loop like this, and then the next loop does the same thing, and the next loop does the same thing, and the next loop does the same thing. What you end up getting is a straight magnetic field through that solenoid. Okay? Which is kind of cool, because basically each of these loops are producing a magnetic field pointing in this direction in the center, and in this direction on the outside. So you end up with straight magnetic fields, which work out cool. So straight currents produce circular fields. Circular currents produce straight fields. Nice little conundrum. All right, now let's look at right-hand rule number 2. Right-hand rule number 2 tells you basically what direction that magnetic field is pointing, or if you know the direction of the magnetic field, what direction the current is pointing. There's two variables, the current direction and the magnetic field direction. Right-hand rule number 1 had F, I, or V, depending on how you thought about it and did it, and B. So right-hand rule number 1 has 3 variables. 2 only has 2 variables. Okay? And this is for when you have a straight wire. Right-hand rule number 2 is for straight wires. Okay? For example, if I have a current pointing down, then my magnetic field goes in this direction. If I have a current pointing up, magnetic field goes in the opposite direction. Opposite direction of the current, opposite direction that the magnetic field turns in. Okay? And we do this by using a thumbs up symbol. Okay, so make your hands into the thumbs up sign. Your thumb pointing up, your fingers curling in. And point it at me, saying, "Yes, Miss Lawson, you're awesome, thank you." Okay, now this is your right hand, by the way. Make sure you're doing it with your right hand. So your right hand has your thumbs up and your fingers curling in. Okay, what you're going to do is you're basically going to act like you're grabbing the wires with your fingers. Alright, so if you take like a pen or a pencil, it's like you're gripping it with your fingers. If you guys have ever played golf, I never really played golf, but they tried to teach me in gym once. And it was along the lines of you curled your fingers around it and then you pointed your thumb straight down. Same kind of idea. Curl your fingers around, thumb pointing straight. Okay, you point your thumb in the direction of the current. And it's in the direction of the conventional current. Which is the way that positive charges will go. Okay? That's the key. Right hand, positive. Left hand, negative. Okay? So, your thumb points in the direction of the conventional current, the direction that the positive charges are flowing, and your fingers curl in the direction of the magnetic field. Okay? So your thumb points in the direction of the movement, saying, "Go, baby, go, baby, go." Okay, sorry. And then your fingers will curl in whatever direction the magnetic field is going. Let's give it a whirl. Draw the magnetic field for a wire with a current flowing out of the page. So if the current is flowing out of the page, then your thumb is going to point out, right? So if you think about it, or if you grab your pencil, alright, point the tip in the direction of the current, so out of the page, or out of the paper if you're looking at a piece of paper, and then say, okay, what directions are my fingers curling? My fingers are curling like this. So that's the direction of the magnetic field. Now, it gets a little bit more complicated to draw when you're looking at a current flowing in a direction. So if my current is flowing east, okay, and I point my thumb east, and I really do recommend you grab a pen or a pencil for this, it helps seeing it. Okay, on the bottom side, your hand is going down, right? Your fingers are pointing down, your hand is curling down. It's curling into the page, or into whatever, okay, into the board. On the top side, on the up side, it's curling out. Okay, your fingers are curling out. That's a tricky one to think about. Alright, but one of them will always be an X and or an O, and the other will be an arrow that you can draw. Okay, because they're perpendicular to each other. So if one is an arrow, the other is going to be an X or an O, and or an O. Okay, That's right hand rule number 2. Right hand rule number 3 goes with that solenoid, that multiple loops in a row that produce a straight current, a straight magnetic field. Okay, so the thumb goes for the straight part, and your fingers go for the curly part. So when we were dealing with a single straight wire, your thumb was the direction of the conventional current in the wire. Now that we're dealing with curly current, your fingers are the current and your thumb is the magnetic field. With right hand rule number 3, you're going to make that same thumbs up sign. Okay, and your fingers are going to curl in the direction of the conventional current. So if we look back at this picture, you see how the current is coming up the front and then curling down behind the back and then up and then down behind the back and then up. Make your fingers do that too. Okay, so your fingers are going to curl up and around, same way the current is going. And then your thumb is going to point towards the North Pole. Okay, your thumb will point towards the North Pole of the magnetic field produced. So your fingers curl in the direction. Once again, a pen or a pencil is very helpful. If the current is going around, like in front and then behind, you curl that way. Okay, now we're going to use this in the opposite way. We're going to say, okay, this is the North Pole, so this is the direction that my thumb is pointing. My thumb is pointing that way. Okay, so if you had a pen or pencil, let's say the tip of your pen or pencil was the North Pole. Point your thumb towards the tip and then curl your fingers around. You'll see that in the front, your current is going up, and in the back, your current is going down. And that's how you draw your current. Alright? The current is going up in the front and down in the back, so your North Pole is to the left. If it was the opposite way, you flip your hands around, and that's the direction of the conventional current. Alright, make sure you complete your thinking maps. Alright, this is just a summary of the lesson. Everything was found there in your notes. If you have trouble, see me before 7:17 in the morning. Good luck on your homework.